Welcome to the Explainer. If you've been paying any attention to AI lately, you know it's moving incredibly fast. It's everywhere. But today, we're actually popping the hood to see what's going on underneath. This is part one, inductive reasoning and the connectionist guess. We are going to explore how neural networks actually operate and learn patterns from just massive data sets. So it all begins with one really fundamental question. How does AI actually think? Now, obviously, most of us already know there isn't some tiny human-like mind at work on the other end of a language model or an image generator, right? But what are the actual mechanics driving this machine intelligence? Well, as it turns out, the way these modern systems operate is fundamentally different from how computers were originally programmed. Okay, let's dive into this. For decades, AI relied on what we call symbolic logic. Think of it as rigid rules, manual logic, and totally transparent decisions. Humans explicitly programmed every single step, like a recipe. But modern AI, it's connectionist. Instead of pre-programmed rules, it relies entirely on recognizing massive data patterns, calculating continuous probabilities, and making these opaque inductive guesses. Basically, it figures things out by looking at vast amounts of examples, rather than following a strict top-down instruction manual. To really understand this connectionist approach, we have to start at the absolute basic building block, the perceptron. It's modeled directly after how our own biological neurons process information, but a perceptron is just a single mathematical unit. Millions of these tiny units work together to learn patterns inductively, and they form the very foundation of artificial neural networks. Let's move to and see how this builds into an actual functioning system. How does this artificial neuron do its job? It breaks down into 4 snappy steps. First, it receives inputs, so data from an image, a word, or even just signals from other neurons. Second, it calculates a weighted sum. Now, this is absolutely crucial. Every connection has an adjustable parameter called a weight that basically evaluates how important that specific input is. Third, that sum passes through a transfer function to assess all the combined inputs. And finally, step 4, it spits out a single output value. As the system learns, it is constantly, relentlessly adjusting those continuous numerical weights to get better at predicting. Now, you might be wondering, why abandon those nice, transparent, hard-coded rules for this wild inductive guessing game? Well, because of the messy real world. The real world is full of tremendous amounts of unstructured data. There are infinite visual and environmental variations. It is literally impossible for a human programmer to anticipate every single fluctuation. Imagine a machine vision system trying to recognize a product from a million different angles and lighting conditions. Hand-coding rigid step-by-step logic for every single possibility? It's way too time-consuming, and frankly, it's just impossible. And that is exactly why this probabilistic prediction model became the gold standard. Think about it like this. Consider the example of driving on the road at night in dense fog. You are very uncertain, right? But most of the time, you manage to navigate without much thought. When we navigate that kind of uncertainty, we aren't calculating precise physics equations in our heads. We're using a mental probabilistic model to make a really good educated guess. AI operates on a remarkably similar philosophical plane. It makes educated probabilistic guesses that turn out to be incredibly powerful in chaotic environments. Now, what's really interesting about this is what happens when you scale it up to a deep learning neural network, say for something everyday like a shopping recommendation. Notice how those single artificial neurons stack together into hidden computational layers. A modern network doesn't just have a few of these. It might have hundreds or even thousands of layers. The output of one layer simply becomes the input for the very next one, refining the probabilities at every single step. All this massive stacking compounds into a seriously high degree of predictive confidence. But here's the catch. This incredible scale and complexity brings us to an immediate, severe consequence: the black box problem. Because these networks have such intricate, multi-layered structures processing vast amounts of continuous data, their decision-making becomes almost impossible to interpret. We know exactly what inputs are going in, and we can clearly see the outputs coming out. But those millions of continuous weight adjustments happening deep inside, they are essentially a complete mystery. Even the genius engineers who build these models struggle to fully reverse engineer the rationale behind any specific output. If your head is spinning a little bit, let's ground this massive abstraction. A fitting metaphor for neural networks would be autocorrect on a grand scale, which relies on optimization algorithms to suit the data. That is exactly what is happening inside that black box. It's not magic, it's just a lumbering statistical engine optimizing itself over and over and over again to guess the next word or the next pixel that best fits the vast amounts of data it was trained on. But that brings us to a rather urgent and honestly kind of wild question. If these neural networks are so incredibly good at pattern matching and probabilistic guessing, why do they hallucinate? Like, why do we constantly see AI systems completely making things up out of thin air? Let's pivot for a second and look at the unintended consequences of this architecture, because understanding the flaws of this system is absolutely just as important as understanding its strengths. So, a hallucination happens when the AI produces false or nonsensical information that appears super convincing but is completely inaccurate and totally untethered from reality. This is a critical flaw, and it happens for one specific reason. The AI operates inductively. Connectionist AI completely lacks strict logical rules. It doesn't have a built-in encyclopedia of true and false facts. All it has are probabilistic guesses based on statistical weights. So when it generates a hyper-confident answer that is dead wrong, it's literally just the math landing on a highly probable but factually incorrect string of words. And the mechanical reason for a lot of these hallucinations is a fascinating phenomenon called exposure bias. You see, when an autoregressive model is generating text, it's predicting just one word at a time. If the model makes a tiny mathematical error or a slightly poor prediction early on in a sentence, it uses that flawed output as the input for its very next prediction. This means the errors snowball. Once the engine derails, it just goes in circles, generating more and more irrelevant or repetitive output, completely without the ability to course correct. So the crucial point is how this compares to us. Think about human correction versus AI trajectory. When humans navigate, we notice when we're going in circles. If we take a wrong turn while driving, we stop, we rethink the route, and we course correct. We have common sense and we can plan non-sequentially. Autoregressive AI models, though, they just continue driving forward. They completely lack the ability to step back and check the route once they've started. They just keep making the next statistical guess, hoping to eventually hit a plausible destination, propelled entirely by unthinking forward momentum. I want to conclude this explainer with a really powerful thought from Noam Chomsky. He says, the human mind is not a lumbering statistical engine for pattern matching. It seeks not to infer brute correlations, but to create explanations. Modern neural networks are breathtakingly impressive probabilistic prediction engines. They handle the messy, chaotic data of our world by adjusting continuous numerical weights to guess the best output. But they are not minds. They find correlations, for sure, but they do not inherently understand explanations. So as these statistical engines grow exponentially more powerful at predicting the exact right next pixel or word, we have to ask ourselves, at what point does a perfect imitation of reasoning become indistinguishable from the real thing? Until next time, keep questioning.